Hello everyone, welcome back to the another session in design and analysis of algorithms. Topic name is 0 by 1 Knapsack problem. This topic you will find in 4th unit and topic number 6. Now, as far as this video is concerned, we'll be going to talk about what is 0 by 1 Knapsack problem. And before of this video, there were 0 by 1 knapsack problems which we were solved using greedy method and brute force approach, and even we were solved the same problem with the dynamic programming, backtracking. There are many things, many algorithm techniques by which we solve this 0 by 1 knapsack problem. So what is the approach of branch and bound to solve 0 by 1 knapsack problem? And we'll also generate state space tree to find the solution of 0 by 1 knapsack problem using least cost branch and bound. Now let's get started. So 0 by 1 knapsack problem. The objective of this problem is to fill the bags with those objects such that the total weights of the objects included in the bag should be less than or equal to the capacity. Now let's see some example. I'll give some example for this problem. So the example is what? There are 4 objects what I'm considering. Now the capacity is m is equal to 15. I have 4 objects to place inside the bag. The profits of each object is correspondingly I wrote 10, 10, 12, 18, and the weights of each item is 2, 4, 6, 9. Now, one more important thing is, if we are taking any object, then we must take the complete object or don't take it all. So that means no fractional part of object can be placed in inside of the bag. So if let us suppose m is equal to 15. So m is equal to 15 in the sense, so I am taking x1 object into inside of the bag. That means m is 15. Now what is the w1, the weight of the first object? 2. So that means 15 minus 2, I'll get 13. So still 13 more weight, 13 kgs of weight I can utilize for the next place item. So now I'm placing x2 item. If I place x2 item, the total weight of the bag now is what? 13. Now w2 is what? 13 minus w2, 13 minus 4, which is 9. So still 9 kgs I can use. Now I'm placing x3 object. So x3, if I place 9 minus 6, it is 3. So now to place this 3 kgs of weight, you will be looking at x4 item, correct? Because you have only 4 items in the problem. So you done with the x1, x2, x3. These are what already available inside of the bag. So to place x4 item, what we will do is, we'll be going to take only 3 kgs out of 18 now, normally. But this approach, this 0 by 1 knapsack problem using branch and bound approach will not take fractional part of weights. Okay, so that is what we have to focus much. Now, so the problem is what? The total profit gain should be maximized. So it is a maximization problem. But in the previous video of branch and bound, we were discussed very clearly that a branch and bound approach is for minimization problems. Now, we were discussed in the previous videos, the other methods are maximization problems. That is what greedy method, dynamic programming, backtracking, all are for maximization problem. Now, the problem is maximization problem, but we are not going to use these approaches. Though it is not minimization problem, we are going to approach branch and bound. Now, very simple to understand it is, we can solve only those problems which are minimization. Here, the answer we want in maximization. What we will do is, we will convert the signs of the profits. Let's see. So in the maximization, I have 38 is my profit. 38 and 32, which will be more maximum, which is the maximum value. So then 32, 38 is the maximum value. Now we'll take this as maximization problem. Now what we'll do in branch and bound to fulfill this constraint of minimization, we'll change the sign of it. Minus 32, minus 38. In these two, which is minimum? Which is minimum? Minus 38 is minimum. Though it is, if it is a maximization, we'll consider 38. If it is a minimization, also you are considering 38. That means we can convert the signs of these profits. Instead of positive, we will make it as a negative weight, negative profit, and can also solve this maximization problem, can be converted into minimization and solve. Then again the result will convert back to maximization, right? So this is how we are going to find the solution for branch and bond problems. 0 by 1 knapsack problem, even traveling salesperson problem also we'll do in the same way. Now as far as this video is concerned, 0 by 1 knapsack problem signs we are going to change to be to fulfill the branch and bond constraint, which is its minimization problem. Now let us see how to solve this problem using branch and bond. Now, so I'm going to generate a state space tree, and here I'll be using LCBB. What do you mean by LCBB? Least cost branch and bound method. So in the previous video of branch and bound, we discussed about there are 3 different strategies to generate a state space tree in branch and bound algorithm. So the first is what? FIFO method. The next is LIFO method. The next is least cost method. So we can take all these 3, but I'm going to take least cost one. The reason why I'm taking least cost is it is what the fastest method. It is what the fastest method. That's what I'm going to take. If you have a question in the examination, then to take FIFO and to solve 0 by 1 knapsack problem, yes, you can do it. If you have a question with LIFO, that also you can do it. And that is the reason in the previous video of branch and bound, we were taken one problem and solved with these 3 techniques. So you can follow that algorithm techniques to apply over here to find the solution. Now, least cost branch and bound is what? I will be exploring that node whose cost is minimum for solving it using branch and bound. For each node in a state space tree, we have to find out upper bound and cost. So we define it as sum of all of the profits. Now the solution for this problem can be written in variable size solution, fixed size solution. Variable size solution in the sense that which are objects I placed in the bag. That means let us see, x1 and x3 is my solution. Then fixed size solution is what? 1, 0, 1, 0. So whichever object is placed in the bag, for that object we'll place it as 1. So this is going to be our solutions. You can use variable size or else you can use fixed size. Now, so I'm going to take sets method. That is what fixed size method, fixed size solution. Now I'm going to solve this problem in this form of solution using LC branch and bound. Now let's go ahead. So now what I'm going to do is will come from the starting. Now, so I'm going to generate a state space tree. Initially you have to calculate the cost function, and you should also know what is the capacity of the bag after placing each item inside of the bag. Now, so make it is a upper value. First of all, upper value is infinite. So find out the upper value. How can I find out the upper value? So this is the formula to find out the upper value. What is the formula? Summation of I is equal to 1 to n, pi xi less than or equal to m. So find out the u value. U value is what? Profit and object. So now profits is 10 plus 10 plus 12. Now it is what? 18. So 10 plus 10 plus 12 plus 18 is what? It becomes 20, 32, 18. 50 is the weight, right? Now listen carefully. If I calculate the cost of it, okay, now cost is what? PIXI, 10 plus 10 plus 12. If I take in this way, this 10 plus 10 is the profit for which item? X1. Now what is the weight of it? 2. This 10 weight is 4. This 12 weight is what? 6. Now let us assume that I have a knapsack. 6 plus 4 plus 10 plus 12. 12 kgs are I have used with this X1, X2, X3. Now how can I place the total total object inside of the bag? I cannot, right? Because I don't have a space. I have only 3 kgs of weight to be used. So, but here the fourth item is having 9 kgs of weight. So, among this 9 kgs, I can take only 3. So, that's what cost function I am going to take with the fraction. And this u upper limit is I am not taking with fraction. So, let's go ahead. Now, if you take out this value from this, now 18 by 9 into 3, that means 6. So, 32 plus 6 will become 38. I told you in the beginning slide, in the previous slide, that the this values has to be changed, sign should be changed from positive to negative. So, now the upper value I am taking with minus 32. This figure you have to take. Why this figure you have to take? Because I am not taking u value with the fraction. So without fraction is what? 10 plus 10 plus 12. That is 32. And c value is what? With the fraction. That's what it is, 38. Now I am going to generate the state space tree. Let us suppose that I am placing the first object. Initially, what the cost you got? Cost is minus 38 with fraction, and upper limit is minus 32 without fraction. Now, when I place x1 object, the same. If I don't place x2, x1, it is second node, it is third node. Assume that I am not placing x1. That means x1 equal to 0. So, in the place of x1 is equal to 1, the same cost and the same upper limit will be there, minus 38, u is equal to minus 32. Now let's see, if I don't place x1 value, then what happens? In both u and in c, you have to take out the 10. So that means if I cut this 10 over here, because S1 object 10 has not included, and this 2 also not included. Now let us calculate the cost and upper limit. So now C is equal to what? X2 object, X3 object. 6 plus 4 is 10. Still you have only 5 more kgs left. So when you have 5 more kgs left, what you will do? Now, that means you will take this 10 plus 12. Now this time 18 by 9 into 5, because 5 kgs only we can use. So it is what? 10 plus 12, 22. 5 into 2 is 10. 22 plus 10 is what? 32. 22 is u value. Correct? 22 is u value. C value with the fraction you can take. That is what? Minus 32. Okay. Now let us have x2 object inside of the bag. So there won't be any change. The same value, C is equal to minus 38, U is equal to minus 32. If you will not place x2, then let's see the value of U and C's. So x2 is 0. x2 is 0 means what? x2 means this 10 will get out of the picture. That means this 10, this 12 will be there. 10 plus 12 is what? 22. Now, how much weight I can still keep inside of the bag? That let's see. This 10 is there, but this 10 is not there. So that means 10 plus 12 is 22. And come here. This 4 is not there. 2 plus 6 is there. 2 plus 6 is what? 8. Still how much weight I can use? 7. That means 8 by 7. 18 by 7, u is equal to, for the value x3 is equal to, x2 is equal to 0. x2 is equal to 0. U value is what? U value is 10 plus, and this 10 you will not take because x2 is not there. 10 plus 10 plus 12 plus 18 by 9 into 7. So the cost is what? 10 plus 12 is 22. 22 plus 7 into 4 is 14. 22 plus 14, it becomes 36. Now when x2 is equal to 0, your u value is minus 32, c value is minus 36. So c is with fraction, u is without fraction. So I am calculating in one equation. So it is what? If you consider this fraction, then it is c value. If you don't consider this, it is u value. Please keep in mind. Now let's go ahead. So here you got x2 equal to 0. Now let's see for x3 is equal to 1. If x3 is equal to 1, then the cost value you please calculate. Then what is the value if x3 is equal to 0? U is equal to minus 32, c is equal to minus 38. Now if I don't place x3 value, that means x3 is equal to 0, then what is the value? That if x3 is equal to 0, u value is minus 38 and c value is minus 38. Now let's see that when I wanted to explore the node according to least case to branch and bound, I have to take least cost, correct? So now I am taking the least cost method. So among these two, minus 38 is the least cost, right? So now I am going to take this minus 38, this minus 38. That means from fourth node exploration will get started. Now the reason I have to update even minus 32 to minus 38 because I got a least number than that, correct? So now here x1 equal to 0, first object is not included in the bag and the cost is minus 32. So this is what minus 38 is the least one, right, than minus 32. So I am using bounding function to get it because I found a cost which is lesser of this. So this cost is greater of the node. So I have to bound it. That means I have to kill this node. The same minus 36. I will be killing this node. So finally I have this minus 38 and this minus 38. So among these two, what I have to place? Now let's think. x3 item, x2 item, x1 item, both items we were placed in the bag. That means 6 plus 4 plus 2, which will give weight of 12. So if I do not place which item? x3 item if I do not place, that means this item. Then 9 plus 2 is what? 11. 11 plus 4 is 15. So it is what? The perfect solution. That means x3, without x3 it is a perfect solution. So we will explore this node to say it is an infeasible solution and we start exploring this node. So in this node, can I have x4 object? That means x4 equal to 1, x4 equal to 0. Now let's see. So when I put x4 equal to 1, then what the value you will get? x4 equal to 1. Now calculate your c and u. So u is what? x4 is equal to 1. That means 10 plus 10 plus 18. Now what is the value? 20 plus 18, which is 38. When x4 equal to 1. That means c is equal to u is equal to 38 minus 38. What is the c? So if you see the profits, if you see the weights of it, you will be finding out perfectly whether it is gives you the what the cost it will give you. That is what? 2 plus 4 plus. So third object I am not including. That's what? x3 is not included. x4 I have to include. So 12 is not required. 2 plus 4 plus 9. So how much weight is still left? 9 plus 2, 14. Exact weight. So you cannot have any fractional part over here. The both are equal, minus 38, minus 38. Now let's see, if x4 is equal to 0, the cost will be minus 20. So it is what the more cost, right? It is maximum than minus 38. So that's what this is the final solution. What is the final solution? That x1 you can place, x2 you can place, x3 will not, and x4 is. That means the solution is what? S is equal to 1 comma. That means x1 object is in the bag, x2 object is in the bag, x3 is not, x4 is in the bag. That's what we were shown with the sets method, 1 1 0 1. Now that final cost of the bag is what? 10 plus 10 plus 0 plus 18, which is 38. It is a maximum value, right? 2 plus 4 plus 9, it is a maximum capacity what we were used. So these are what the respective U and C values to each node what we were solved in the previous slide. So this is what knapsack problem using branch and bound. Thank you all.